I'm Ferenc Krausz. I'm director here at the Max Planck Institute of Quantum Optics and have chair of experimental physics at the Ludwig Maximilian University. Our main goal is to gain ever deeper insight into microscopic phenomena that profoundly affect our life. The key players in these phenomena are electrons. Electrons affect our life in incredible many ways. Of course, via all the electronic gadgets that our modern life is based upon, as well as actually the way our organism is functioning is all about electrons. Electrons form the glue between the atoms that actually create the molecules of each and every living organism. Our microscopic world is very seldom static. In most cases, our microscopic world is in motion. No matter how high the spatial resolution of a conventional microscope is, can such a microscope capture the dynamics that occur all the time in the microscopic world? To be able to freeze the motion of the fastest particles in our world, we need to be able to do microscopy in time. And that's exactly what we can do with short laser pulses. We are now entering the area where we are doing our attosecond photography of the microscopic world. Here you see three what we call attosecond beamlines, which are our high-speed cameras. If the exposure time of your camera is too long, then the fast-moving object will appear on your picture in a smeared way. In a conventional camera, you have a mechanical shutter which kind of opens and closes, or you can also do this electronically, but in any case, you can't become much faster than a microsecond, about a millionth of a second, right? These are the fastest cameras which can actually even capture the motion of a bullet from a gun. Yeah? However, this technique cannot be developed much farther, and you have to come up with some new idea. And this new idea are flashes of light. Basically making very short flashes and illuminate the object you would like to capture, the motion of which one would like to capture with a very short flash. And this is only possible with lasers. The trick to generate them is that actually we make the laser emit continuous waves at many different frequencies in such a way that at a certain instant in time, the maximum of one of the oscillations of each of these waves of different frequency coincide. And that's the moment when, correspondingly, the sum of all these waves builds up to a very high intensity, and this is the peak of the pulse. I guess everyone has heard about the time unit nanosecond, which is a billionth of a second. Now, if we move towards shorter time scales, the first are the picoseconds, which are 1,000 times shorter than nanosecond. Then another 1,000 times shorter are coming the femtoseconds, and yet another 1,000 times shorter, we move into the world of attoseconds. So one attosecond is actually a nanosecond, 1 billionth of a nanosecond. And from our laser laboratory above us, the pulses are coming down through this evacuated tube.
are directed into that very box over there, where we can decide which of these 3 beam lines is being served with these laser pulses, and which of the 3 beam lines is actually used for an experiment.
By interference between the light waves, we can get down only to the femtosecond regime, because light wants to be a wave, and therefore we can't compress the duration of this radiation to a time interval shorter than at least 1 wave period. So this is still not short enough to actually capture electronic motion. So we asked ourselves, what else can we possibly do to generate even shorter flashes to be able to capture eventually the motion of electrons? And the idea was really intriguingly simple. Just make sure that such a single cycle laser pulse, it has a strong enough electric field that it is able to rip off 1 electron from an atom. And this procedure of ripping off the electron requires the electric field to overcome a certain threshold. So if you now imagine this electric field in our short pulse has basically a single half cycle in the center, and then only a small fraction of this single half cycle delivers strong enough electric field for this process to activate. And therefore, this ripping of the electron can happen within a fraction of this half cycle of our laser pulse. And this fraction actually means a fraction of a femtosecond. So we indeed managed to generate in this way extreme ultraviolet flashes of light. Back in 2001, turned out to be 650 attoseconds. So the field of attosecond physics was born.
The actual interaction region where the photography, the attosecond photography takes place is actually really very small. We need to build a big apparatus starting with the laser, then with the attosecond pulse generation, and with all the degrees of freedom to actually manipulate these 2 beams to eventually be able to investigate the processes in a tiny little volume that is a really tiny fraction of the size of the whole infrastructure needed for that.
Of course, we can't see the electron itself because it's that incredibly tiny. We can just measure the properties of the transmitted flash of light and the electrons with which this very short attosecond flash interacts leaves its imprint on the transmitted flash of light. So if we analyze this transmitted flash of attosecond light, we can learn about the instantaneous state of the electron at the very moment of the flash.
When we perform a new experiment, it's and we see first outcome of that experiment, the kind of feeling that we are just seeing something which no one else, at least on this globe, has ever seen. It's a very special feeling which is really hard to describe. I don't think it can be compared with any other human feeling. And I can tell you that it is still the same feeling as it was 20 years ago. It's a kind of childish joy and pleasure that we now again entered some uncharted territory and may have the chance to understand something that no one else has seen before, has understood before.
We have been doing this research on fundamental phenomena for about a decade. We actually recognize that the number of new questions and new effects are not getting smaller. So having convinced ourselves that the method is working well, we thought, okay, What are electrons actually, what can they be good for that could possibly serve some practical purpose? One obvious answer is they are carriers of electric current, right? So one way of boosting the power of current generation classical computers, just speed up the switching on and off of electric current. In this way, you could just perform more operations within the same time. So your computer would be more powerful. Just think of our fuse cycle laser light. This contains the same kind of electric field that is being used for switching on and off current also in circuits. And we have started doing research in this with our attosecond tools, and it looks like that potentially we should be able to boost the power of current computer technology by a factor of 100,000 approximately. This is one direction. Attosecond technology also offers us to use a very short burst of well-controlled infrared waveform to bring a molecule into vibration, or a set of, or an ensemble of molecules into vibration. And then the second job that attosecond technology can also do is to actually sample the infrared waves that these vibrating molecules send out in the wake of a very short excitation.
And this is our laser-based molecular fingerprinting instrument of the first generation. The system starts with a laser oscillator that generates a very short femtosecond duration laser pulses. And this laser pulse trans-illuminates our biological sample. In our current experiments, these are samples of human blood, human sera, or human plasma samples.
So when we have an infrared source which contains all the necessary frequencies, and that's what we are working on, we could actually address all molecules present in a complex biofluid like human blood. All the tens of thousands of molecules. It's not so much the very composition that we are interested in, but more the change, because if we could measure changes in the molecular composition precisely and could bring it in correlation with changes in the physiology of the organism, then this might be a possible way of actually diagnosing a disease that is just about to emerge.
Here you see the heart of our molecular fingerprinting instrument of the next generation. As you see, it is much more compact than the instrument that is currently in use. It also offers a broader spectral coverage, so we will be able to measure a larger fraction of the molecular fingerprint, as well as offers higher sensitivity. And most importantly, it's going to be more user-friendly. So it's a first step towards clinical applications.
Our research could not exist without the participation and contributions from people all over the world, and each and every student, each and every postdoctoral research fellow makes a very important contribution. So we can offer a lot of problems to be solved, and whenever we are able to overcome one, this always allows us to move into new territory, which may open up exciting applications.